Good afternoon, all. Actually, there is some change in the schedule. Faculty of Geosciences, who supposed to deliver a lecture today, not available. So this lecture was scheduled on Wednesday. So application today we will discuss instead of Wednesday. Today we will discuss about the application of GNSS in atmospheric studies and the GNSS reflectometry concepts. So till now, you have learned about the basics of the GPS, which generally used for precise positioning. We are going for survey. We are collecting data for the position for various GIS applications or maybe remote sensing purpose. Now, the other aspects of that GNSS signal is that we can utilize the GNSS signals for the atmospheric parameter retrieval, like a precipitable water vapor. So we will discuss in detail that precipitable water vapor, how we are deriving using this GPS data. Now, this GPS can be installed at ground, which or using this we can continuously take the measurements of or at a particular point, or this GPS also can be placed on a satellite. The receiver, the means the sorry the GPS means the GPS receiver can be placed at a ground, or it can be placed at a satellite. So when it is a placing of satellite, in the sense when the altitude of the GPS satellite is 20,000 kilometer, and generally normal low earth orbit satellites are orbiting in around 700 to 800 or 600 kilometer altitude. So this always will be on the top 20,000 kilometer and the GPS satellite, and the low earth orbit satellite always will be on the lower side. But this is also revolving, and this is also orbiting around the earth. So whenever when we are putting a GPS signal onto this low earth orbit satellite, it will also receive the signal from the GPS satellite, and continuously it will maybe for some time, and after that it will be setting on a earth's other side, and it may not be the receiving the signal after some time. So we can place a GPS receiver on this satellite as well. We can place the GPS receiver at ground. Ground we have two types, like one is static and another one is a dynamic. Okay, so we will discuss about these things. And third is the basically the concept of the reflectometry. So signals, whatever it is coming from the satellite, is not only directly when it is coming from the means satellite to the receiver, it will pass through the atmosphere, so it will carry the information of the atmosphere. But when it is reflected from its surface and then it is received by a receiver, so it will carry the information of the reflected surface, the surface. Okay, so that way this basically the reflectometry concept comes. So we can use the direct signal also, we can utilize the reflected signal also for retrieval of the parameter. Okay, so in traditional GNSS applications, signals arriving at a receiver's antenna from nearby reflecting surfaces multipath or interfere with the signals received directly from the satellite, which can often result in a reduction of position accuracy. So what is happening when this reflected signal interfere with the direct signal, or direct signal is also when it is coming to the receiver, it is affected by a basically troposphere or the ionospheres. Errors are there. So delay will be caused, and then because of that delay, the position accuracy will suffer. By properly processing the scattered signal, this system can be configured either as an altimeter or a scatometer, allowing us to estimate characteristic of land or ocean surface, such as height, roughness, or dielectric properties of the underlying media. Using various methods, the atmospheric and the geophysical parameters can be estimated, such as water vapor, total electron content, mesoscalation topography, ocean, water surfaces, wind, soil moisture, vegetation, snowpacks, water surface elevation, and sea ice. So the GPS signals will be more useful for the retrieval of these parameters also. Okay. Depending on the platform of the GNSS receiver, stationary, airborne, or spaceborne. Stationary means we are fixing at the receiver at the ground. Airborne, we can fix it on the any air bodies, air vehicle, or any instrument, or spaceborne means or putting on the satellite. The capability of this technique and specific method for processing of the reflected signals may vary. So the whatever the means the signals we are receiving, whether it is a reflected way or directly, the processing will differ from one to another. So as we told, the space and the ground based GNSS receivers. So first we talk about like when we are fixing at the ground, as I told you, where we have a two type of receivers, like static and the dynamic. Static means like a continuous operating reference stations are there. These station, in that what will be that the receiver will be fixed at the ground. We have an international GNSS service around the world. Their GPS stations are installed. That's a fixed stations. In India, generally we have a two stations like in Bangalore, IISc, and Hyderabad. So we are fixing. There is one IGS stations are there, and apart from these IGS stations, the IGS stations data freely available. Apart from that, we have a means stations, course stations from the various agencies. Maybe like we have our own course station at our IIRS, and we receive the continuous measurements, continuous data from the GPS satellites. Our receiver receive. So these receivers will be fixed at a particular point. Now static receivers, why we need, because we need continuous measurements. So there is at a particular place, so that's why we are going to fix this receiver and we will receive the continuous data, so we can find out the information of basically that atmosphere of precipitable water vapor estimation continuously at a particular point. Or dynamic, generally we are using for the basically survey purpose or positioning, so maybe collecting a data for a shorter duration and then we can use it. Okay, this is the basically ground ways. Now apart from that, now we are fixing our GPS receiver to the first on the space bodies, means like a satellite. As I told you, it's a 20,000 kilometer GPS, around 20,000 kilometer GPS altitude, and then lower altitude it will be around 700 to 800 kilometer. So it will continuously receive the signals from the maybe GPS satellites, but since the motion is there, that is also moving the low earth orbit and the GPS is also moving, so it may be for a shorter duration, it may be receiving the signals, and then it is maybe it will come on the earth's other side and it may not receive the signal. But while in case of the static receiver on the ground, so it will be continuously from 0 degree to it will be receiving the signals, and then satellite will be orbiting and then it is going, and then other side it will be setting. So the receiver will be at the fixed place, but the GPS satellite only will be moving and going on to the other side. So 0 degree elevation to the another side, 0 degree elevation it will be there. While in case of space based, it will be both will be moving. So both satellite and that GPS satellite and the low Earth orbit satellite, both movement will be there. Okay. Now, two types of analysis possible using the basically GNSS signals. One is using the direct signal. Another one will be the using the reflected signals. So direct signal, when it is coming from a satellite to the GPS satellite to the receiver, it will pass through the, it's not means affected by the any surroundings or bodies. So directly when it is coming from GPS receiver to the, GPS satellite to the GPS receiver, then it will come through the ionosphere and the troposphere. So ionosphere, when it will pass through the ionosphere, it will carry the information of ionosphere, or it will be the delay will be there, or because of that ionosphere. Okay, electron content. Now secondly, when it will pass through the troposphere, it will carry the information of the troposphere, or the delay will be there because of that means is troposphere. So what will happen when we are able to estimate this delays? There are two things. One is the basically when we are using the models, we are removing that delay from that to make it like a straight position, the geometric distance between the means satellite, GPS satellite to the receiver. Okay, so if you are able to remove this delay, whether it is an ionospheric delay or tropospheric delay, it will be a basically geometric distance, means just a straight line distance. And because of this delay, instead of geometric distance, it is becoming a curve. It is becoming a curve. Okay, because that delay is happening. So if you are able to remove these delays, then it will be a basically straight, the geometric distance will be there. Now if you are if means the delay information, so that geometric distance will be basically used for the basically precise positioning. If we are able to correct remove these delays correctly, then the our estimated position will be more precise. Now secondly, if we are able to know these delays from this data, uh, from the data, okay, so now we are not using these models. Now from the data itself, we will deriving the delay. So if we know the delay, then we can estimate the atmosphere, like because of what this delay is happening, this post neutral atmosphere, this delay is happening because of the two things. One is the basically hydrostatic or the dry delay. Another one is the basically called the wet delay. So there are the two parameters. Because of this delay is happening. So if we are able to estimate these delays. So if we are able to know the hydrostatic delay or the wet delay, so wet delay, if we are able to know, we can derive the from there that the how much water vapor content or means in the atmosphere it is present. Okay, so this is the basically analysis using the direct signals. So direct signals can give the two things when when it is a basically water vapor content, and another one is the basically total electron content. Now the second thing is the reflected signal analysis. Basically it is for the basically earth surface studies. Now from when the signal is coming from the satellite to the receiver, so there are the certain means signals which will not directly come to the receiver. What will happen, these signals will basically come from the, so we were discussing about the basically static and dynamic receivers, and then after that use application of the direct signals, and we also discussed about reflected signals application when the signal is reflected from the surfaces, whether it is a soil moisture, from the basically ground, from where we can find out the soil moisture, and from the surfaces where the snow it is there, so we can find out the snow depth or the water level. The only thing is that we were discussing that there should not be nearby like buildings or any other means obstruction should be there, so the signal, if it is reflected from the different bodies and then it is received by a receiver, may not be the correct estimation will be there. So we are going to place a receiver in such a place where the obstruction is there, not there nearby, so only the possibility is there when the signal is reflected from that surface and it's received by a receiver. So application of GNSS signals, when we talk about the remote sensing of the troposphere and the stratosphere by gauging the refraction, slowing or bending of GPS signals that propagate through the atmosphere. So the study when we do this of in the atmosphere is called the basically GPS meteorology. uh, we are determining the pressure, temperature, humidity, and depending on the location of the GPS receiver, two approaches basically in the GPS meteorology it is there. As we discussed, one is a ground based, another one is will be the space based. So there are the some positive and the negative of what we can say, both the sides when we do. Like we are retrieving here in the precipitable water vapor, it yields a time series of PWV for local observing GPS ground stations. Horizontal distribution possible with a dense network of GPS stations. That means if you are using a GPS station or course station at a particular place, so it is giving a point estimations. Now, if you are you want to do analysis for the wider area, so you need to place the various different stations, more stations that way. So then only this analysis or what we can say, the prediction when you do the application of this water vapor on the numerical prediction, weather prediction, or maybe for other atmospheric studies when you do, then it will be more useful. So alone single placing a particular station can give the information only means at a particular area only, very limited area. Okay, so we need a dense network of GPS stations. Vertical integrated quantities, lateral gradient of PWB possible. Here continuous measurement at a network of a station, thus giving it time series data. So that's what as it discussed, it's a beneficial for us when it will give a continuous measurements. So continuously we can measure the means parameter at a particular point. So for the years, 2 years, 3 years time series we can define derive, and means we can compare for the basically other parameters, means for other analysis this can be used. Sparse PWB information over oceans. Now the thing is about the oceans. You can place this course at a ground. So this is basically fixed over the ground and continuously measurements you are getting. But about over the oceans and means like a sparse area where it will be means we cannot fix course kind of things. It will be, may not be that much easy here. So similarly here, the other side, if we see GPS meteorology is space based, we can say. Okay, so it yields a vertical profile of temperature, pressures, and water vapor, partial pressure, water vapor, partial pressure by radio occultation phenomena. The technique is called the basically radio occultation. I will come to that point. Global coverage. Now, since it is a space based, and space, what is happening? We have a one satellite, low earth orbit satellite, it is orbiting around the earth, which is orbiting around the earth, and the globe means the earth is also moving. Okay, 24 hours it is taking now, so that is also revolving and this is also moving. So what is happening? So we can get the measurements over a different locations at. So this is a benefit in this case, but thing is that continuous measurement we cannot get. Okay, so global coverage enables a study of global distribution of temperature and humidity over a time period. Continuous measurement at location may not be possible in this case. Vertical structure of atmospheric temperature and humidity we are getting different layers in this, even over the global oceans. So here the benefit is that over the oceans also we can get these parameters. We generally derive this PWB using the means ground-based GPS observations, and principle of ground-based GPS GNSS based meteorology. Error sources in the GNSS signals. First we basically see that how much error is there in the GNSS. Like as we discussed in the GPS, the delay is basically caused by troposphere, ionosphere. So troposphere, the delay is basically for two types of tropospheric delays are there. One is a basically hydrostatic delay, and another one is a basically wet delay. So we can correct all means errors like clock errors are there, and receiver clocks error or satellite clock errors are there. And then we model the zenith tropospheric delay, and we know these type of errors, and we estimate the ZTD, and from that we are estimating the precipitable water vapor. And applications, we use this information in the assimilation of estimated PWB numerical weather prediction models for rainfall prediction, its impact on the climate change, and to study the hydrological cycle more effectively. GPS, global navigation satellite system receiver, have been used to estimate vertical water vapor content for over 2 decades. And basically, a National Oceanic and Atmospheric Administration has a network of around 400 stations, and mostly in North America, that deliver operational water vapor estimates. And EMUTSAT UMETNet GPS water vapor program has over 100 stations shown to improve numerical weather prediction used for basically studying diurnal variation of the water vapor. So advantage of GNSS derived VWB is it is unaffected by the basically cloudy conditions and high temporal sampling, and accuracy as good as better than infrared microwave satellite sensors. And the disadvantage we have, as we discussed, like we have only point measurements and maintenance, data collection, quality control. So the measurements whatever the GPS receiver collects are the basically pseudo ranges, and the code measurements and the dual frequency. 12 carrier phase we have we also receive, that is in the basically dual frequency. And usually the processing is done using the network of receiver rather than a single receivers. So we use the basically not only single receiver, we are using the network of receiver, like when we are processing a data, we can take the nearby IGS stations data for the basically clock corrections, or we use the different satellites, whether it's the correction in the satellites and clock or receiver clocks. So we are using the basically the different stations data. Satellite ephemeris information is there. For GPS, precise ephemeris information is available, and it is used for the basically science applications. Now, GPS receiver generally receive the GPS satellite ephemeris information. What is this ephemeris information? It's basically involves means in that information the orbital parameters of the GPS satellite. So it will be like a, even epoch will be there, year, month, hour, minute, second, millisecond kind of things. And then after that, that's a semi-major axis information will be there, eccentricity information will be there. So all the things, whatever it is related to the orbit parameters of the GPS satellite will be available in that information. You can also propagate using the epoch and the orbital parameter, that information to a particular epoch whatever you want, because in that information maybe you will be getting at like 2 hours, after that it will be changing that information. So you can utilize you can if you want to propagate at a particular epoch, so you can just like a 2 hours 00 UT you are getting, and after that if you want to 001 UT you can propagate it that information also. Okay, so in that basically the orbital information will be there. Now what are the error sources are there? So GPS GNSS signal propagation is tropospheric and the ionospheric conditions. So total if you see that the observed range, whatever the you are getting the total range, how you are getting the range is basically the time delay multiplied by the velocity of the light. So time delay, how we are finding that the receiver is satellite is sending a signal at a particular time, and then it is received by a receiver at another time. So t plus delta t, suppose time is receiver, so t plus delta t minus t, that you take it as a delta t. Delta t multiplied by the velocity of light, c. So it will be the basically the range, the total information. Now the total range will be equal to the, but this total range, how it is coming, it is coming through the ionosphere or the troposphere. So the delay is, it is there, or because of the satellite clock error or another error, this will be there. So this total range is the basically combination of true range plus ionospheric delay plus tropospheric delay plus ephemeris error plus relative clock bias, and the some noise also will be there. So for meaningful accuracy, need to account for hardware biases, cycle slip detection, multipath detection, correction for R tides, ambiguity fixing, statistical modeling to separate different components. So one side, we know that the what are the measurements we are receiving in the our receiver. So receiver, what we are receiving, that's the one is a basically pseudo range, directly range information, and the satellite GPS satellite information. Okay, so one is a receiver information, that's the one from the whatever the time it is delayed, and the signal is transmitted, whatever it is received. So that's information will come into the pseudo range. Then the second one, it is coming from the basically the information is the GPS satellite information. So GPS satellite, when transmitting any means the orbital information of the GPS satellite, it will come into that. Now what are the error sources are there, that's another thing. So whatever the data is there, we need to remove these errors. Okay, if we are removing like ephemeris error, ionospheric error, or the clock biases, everything we are the left part is the basically the tropospheric delay. Okay, so ionospheric error are mostly cancelled out using the dual frequency differences to the first order iono delay inversely proportional to the f square. Code carrier combinations also used to eliminate residuals ionospheric errors. Satellite clock errors eliminated using differences of measurements between two receivers. So that's what we are using, the two receivers. So network, as I told you, the network of stations we need. So satellite clock error can be eliminated. Receiver clock eliminated using difference between the two satellites. So when receiver if having any problem, so we are using the two different satellites information at a particular place, we are removing these. Using these and other corrections, land tropospheric delay can be eliminated. So we are using the Bernice, Gamut, Gypsy, where the various softwares are available. So just to tell that how we are estimating the GPS derived the specificable water vapor. If you see here, we are processing the first the data, GPS data. The data is available in the Rhinex format. Basically, it is Rhinex, various versions are available, and the data will be available in this Rhinex format. From you can download it for these IGS stations, which are freely available, and from that we are estimating the tropospheric delay. This delay further this zenith tropospheric delay is the basically combination of, or the means what we can say, it's means two things are there in which are one is a basically the zenith wet delay, and another one is the zenith hydrostatic delay. There are the two components are there. So for PWB estimation, from this zenith tropospheric delay, we are subtracting the zenith hydrostatic delay. Okay, so zenith hydrostatic delay, how we are obtaining, by using the external ZSD models. So these ZSD models we are estimating using the maybe you can utilize the maybe reanalysis data, or maybe more accurate if you want, like I have written here NCP, which is a basically reanalysis data which is available. you can maybe the grade wise data it will be available, and you can take it any real analysis data, and it may not be possible to get at the particular location. So what you can do when you have a graded data, you can interpolate at a particular point. Maybe it's a vertical interpolation, or maybe a horizontal interpolation. So you can interpolate at a particular location wherever the coarse receiver it is there, and then you can estimate the zenith hydrostatic delay. You can also utilize the maybe AWS data, met sensor data, which is near to the coarse receiver, and you can utilize its data for basically estimation of the zenith hydrostatic delay. Then finally you can subtract it from the zenith tropospheric delay, and you will be getting finally a zenith wet delay. And that zenith wet delay will be maybe by a constant. You will be multiplying by these one constant, and you can get the basically PWB or at a particular point. Okay, so we can validate with the IGS. When you are deriving the ZTD, you can validate always with the maybe IGS products as well. IGS products are available, and whatever you are deriving at a ground, you can compare it with the IGS products as well. And to derive this, you need some precise positioning of GPS. So you can take it from the IGS services are there. They are providing the maybe so precise coordinates. Maybe after some time it will be available. It may not be available at a particular times, because they are collecting a data from the various reference stations, and then they are doing the what we can say orbit determination, or analyzing the orbits of the GPS satellites, and then they are posting the basically precise position of the GPS satellites. So that way we can define maybe the PWB using the GPS data. And finally you can validate it, we can validate it using the maybe the radio sounded data, or maybe the real-time data, any satellite data. You can verify it whatever the products you have generated. So that way generally there are the some results which I am going to show you. We have a IGS stations here over Hyderabad and IISc, and we have a one course at Dehradun. And so we have, these are the basically tropospheric delay, zenith tropospheric delay for the Hyderabad stations, and one is for the basically IISc. That's basically one another what we can say IGS stations it is there. So you can see that IGS, the red one is the basically IGS ZTD, and which we have taken directly from the IGS products, and one is estimated at the local maybe at IIRS. And then if you see the difference between the IGS ZTD and the estimated ZTD is basically less than 10 mm. If you can see that 10 to 12 mm it is there. So very good estimate we got here for these IGS stations. And then these from that we have derived the ZWD here, that is the basically zenith watt delay, which we got after subtracting the hydrostatic delay from the zenith tropospheric delay. And these delay for the hydrostatic delay we have used the basically presently the NCEP reanalysis data. However, we can also use the AWS or any other data which we are getting from the met sensor, or you can utilize the satellite data as well. So but data should be, if it is a more accurate, then it will be good estimation of the ZST will be there. So when you can, we can see here after getting the this ZWD we have received in the green one, that is the NCEP derived. And we have also derived this ZWD from the various other sources as well. And then we can see the difference is very less it is there. And for both the stations, Hyderabad and the IISc IGS stations. Now secondly, if you see the PWB estimated from this ZWD, This in the right side, two pictures are there, figures are there. One is for Hyderabad, another one for IISc. So very good estimations we got for both the stations, and the difference is there. We're around 2 to 3 mm. The one, oh, sorry, for the 2 to 3 for the IISc for some of the places, some of the days for the year. 2019, this exercise was there, and so the same process we have applied over the Dehradun, and Dehradun CORDS, we have a one static receiver, that is a CORDS which we have established here, and using the data, means the collected data for 2019, and using the NCEP data we have estimated ZSD, and then we subtracted, and then we found this, we have estimated this precipitable water vapor for the year 2019. So we can see clearly that's in monsoon season, around day number 150 to 300, around it is there 180 to 300. It is going very high. It's a 60 pwv value it is going, and the Mera PAW, we have compared it with the basically Mera, that is another real analysis data. From there we have taken, and you can see here 1 or 2 difference only it is there, and it's following the same pattern whatever it is with the Mera it is there. So that way we can derive the precipitable water vapor using the GPS data. This exercise done using the GPS data. However, there are the various other constellations available like GPS, GLONASS, Galileo, and nowadays means number of sources are increasing. So we can continue with this. We can utilize the other sources also and derive these parameters. There are some other results which I am showing. This is how at all from this we can see that's basically whenever they have done the analysis using the PWB and the correlation with the precipitation. So whenever this PW is increasing, and we can see the plots that the precipitation is more likely to increase in the it's going on this right side, see the 10 or it's going higher. Similarly, there's one more study, it was done Manandar et al 2019. If you see the latest, it was there. So they have also done the correlation with the PWB and correlation and the with PWB and the rainfall. Okay, so we can utilize this PWB for various atmospheric studies like numerical predictions, rainfall studies, other things. So GPS gives till now we will be seeing only the GPS is providing the positions. Apart from that, it's more useful for the other parameters also. There was another techniques, that was the radio occultation technique. As we will take few basics concepts, we will discuss about here the few basic concepts of this technique also. When we discussed in the beginning that we are going to put this receiver on a ground base, this receiver whether on the ground, or we are going to put this receiver on also in the space as well. So when we are putting this receiver on in space, means like in low earth orbit satellites. So GPS altitude is 20,200 kilometer, and the low earth orbit satellite is around 700 800 altitude. So when we are fixing this receiver onto the low earth orbit satellite, it will also will receive the signals from the uh, GPS, but for a shorter duration. It is not like a continuously when we are we are measuring on the ground. So occultation means, as you know, that's astronomical or planetary occultations. We are seeing the eclipse. The moon is coming in between, and then this eclipse is happening, solar eclipse is happening. Similarly, the asteroids are occultation of distant stars are there in between. Asteroids are coming. So we know the concept of the occultation. Similarly, we are further extending this concept to the for the radio signals. So occultation is defined as the physical appearance of the objects in the background by the eye and object in the foreground apparently larger. It may not be the larger, but it appears larger during the passage of one them against the another. So there are the some events like these eclipse are there. These are the non-maneuverable. These are non-maneuverable. We can't avoid these. Okay, it will happen, and far and few in between. It's like maybe eclipse is coming maybe once in a year, or maybe these events can happen after some time. It's not like regularly it is happening. Okay, so radio occultation stands for the occultation of radio signals transmitted by intervening astronomical bodies having essentially an atmosphere with the signal received through the refractive bending. So here what we do, the signal, if you can see that, so signal is on this side, so we low earth orbit satellite is this side and GPS is this side. So what will happen, this is receiving the low earth orbit satellite is having a one receiver, and it will continuously receive the signal from the GPS satellite. Now when it comes into the ionosphere or the down, it is a neutral atmosphere. When it is coming, the signal is bending. Signal, it will not be received as in a straight way, so it's some bending will be there. So occultation will come, and this the after some time satellite will be on the other side, and it may not be visible directly to the GPS satellite, but through the bending signal, it will be receiving the signals will be receiving through a one bend. So because of that atmosphere or the ionosphere, it will be bending. So this involves the basically the radio transmitters, artificial satellite constellation of it, and defined trajectories depending on the area to be remotely sensed, and customized receivers are there, either terrestrial or space based here. And so rising or setting of low earth orbit satellites with respect to GPS is called the basically GPS radio occultation. A ray passing through the atmosphere is refracted due to the vertical gradient of refractivity density. During an occultation around 3 minutes, the ray path slices through the atmosphere. So raw measurements changes of the delay of the signal path between GPS and low Earth orbit during occultation. So why this is important, as we discussed in beginning also, it's highly accurate, it's high vertical resolution we are getting, and 100-meter around near surface, and in all weather it will be working. It's not like affected by clouds and maybe aerosols or precipitations. uh, Independent height and pressures which it is of, and independent of radio sonde calibrations, and no instrument drift, and it is not costly also. This is one more important thing. We can take the receiver and place at low earth orbit satellite, and it can profile the ionosphere, stratosphere, and the troposphere. So we know about the GPS constellation. We have around 24 satellites, but so there are some redundant satellite also as well, and they are having an inclination around 55 degree, and semi-major axis is 26,561. So if we see the altitude, because it is orbiting in a elliptic way, elliptical path, what we can say. So maybe around the earth, when the satellite is revolving, it looks like it's in a circular position, circular orbit, but it is not a circular orbit, it is an elliptical orbit. Definitely there will be some eccentricity. So semi-major axis, so when we see the from the ground, it will be around 20,200 kilometer, it will be there. Eccentricity, it's a nominally it equals to zero, but it may not be exactly zero. It's maybe generally it's 0.02. That's what I told you. That's E may be having some value. So when E is there, then definitely it will be on the elliptical path. Apart from GPS satellite, there are the other GPS constellation. There are the other constellations as well, like GPS, GLONASS, Galileo. So various sources are available. So if we put a receiver on a maybe what we can say low Earth orbit satellite, and if it is a capable of receiving the signals from not only GPS satellite, maybe it's from Galileo, GLONASS, or a other constellation, then it will be good. We are receiving a lot of information about the a lot of soundings we are getting. Okay, so we receive what we do. That's a total path delay, as we discussed. It is a basically combination of vacuum path length plus measurement noise. Measurement noise is a combination of what noise contains the receiver and the thermal noise, and this is a basically excess delay, extra delay due to the neutral atmosphere. And from this we are excess delay due to the total delay is basically because of the neutral atmosphere and the ionosphere, and we remove this this is a combination of the neutral atmosphere delay and extra delay due to the ionosphere function of the basically total electron content, d into tec divided by f square. So atmospheric reflectivity based on the precise measurement of the phase delay and amplitude we can derive. So what we do in the data processing, we take the data and raw measurements of the phase of the basically two signals, whether it is a L1 or L2. And when we do the clock corrections, orbit determination or geometric delay, whatever it is there, that we do the clock correction and we derive the bending angles using this. So bending angle of L1 and L2, alpha 1 and alpha 2, and from that we are doing the ionospheric correction, and then we are deriving the neutral bending angle alpha. From that we are doing the Abel's transformation, and then we are performing a refractivity n, and this refractivity n is the basically function of the t, pw, and the p. So correction of clock errors and relativistic effects on the phase measurements, time corrections, compute the Doppler shift and change of phase in the time during the occultation, remove the expected Doppler shift for a straight line signal path to get the atmospheric contribution, ionospheric plus neutral atmosphere, and the atmospheric Doppler shift is related to the known position and velocity of transmitter and receiver. So first compute the bending angle and the impact parameter for each GPS frequency. And for neutral atmospheric retrieval, compute linear combination of alpha and alpha 2, so bending angles for both the what we can say frequency, to remove the first order ionospheric bending and get the neutral bending alpha A. For neutral atmospheric retrieval, the bending is used around 50 to 60 kilometer. For ionospheric retrieval, the bending from each frequency is used around 60 kilometer. So retrieval profile of alpha A during the occultation. So we can see here that when we retrieve the refractivity, it is a function of pressure and temperature and water vapor pressure. Okay, so we can derive, once we know the refractivity, we can derive the other parameter as well. So we have a various missions are here, like megatropic. We have a rosa payload, and in that since megatropic what we can say inclination is around 20 degree, so it's a more useful what we can say to the near equatorial region. So whatever the soundings or the impact points will come, that will be around, it will be varying around the what we can say near to the equator, plus or minus 20 degree. So if we want more observation over the Indian region, and then we can design such a orbit, and then we can get more and more sounding. And if means all over the globe, then we can go for the like a sun synchronous kind of orbit, and then means globally means measurements we can get it. So GPS radio occultation technique is a very promising atmospheric observation system of both weather and climate. It's a high vertical resolution, high accuracy, all weather, and no instrument depth. GPS RO data will be valuable to climate change analysis, validating of climate simulation, operational weather predictions, ionospheric research, and space weather forecasting. The So this was about the space-based and the ground-based, what we can say, the receivers. Okay, so one place we have put our receiver at a ground, and we have estimated the precipitable water using this. Okay, you that continuous measurement. Now, secondly, we have placed our receiver onto the low Earth orbit satellite, and we got the information about the atmosphere, whether it's a at ionosphere or the whether it's a troposphere. So now we that's another thing is that, but these both applications were using the in these both applications we were using the only the direct signals. The signals means directly it will coming from receiver to the what we can say to the from the GPS satellite to the receiver, whether it's a ground or space based. Now second thing is that uh, from the GPS satellite, when the signal is coming and it is reflected from the surface. So when it is reflected from the surface, it will carry the information of the surface as well. So this time the signal will not come to directly to the what we can say to the receiver. It will be coming from the reflected. Now when we are going for the precise positioning, so there is a concept of multipath signals. So multipath signals, when we are removing, because why we are removing, because we need to get the precise position. Okay, so precise position means where the only the direct signals, whatever it is coming from the GPS satellite to the or GNSS satellite to the receiver, we will be using. Multipath means it's maybe the signal is coming and it is suppose hitting any building or any pole, and when it is basically what we can say hitting ground, and then it is received by a receiver. So different path it is following, and instead of that, if uh, directly it is coming, it will be more accurate. So we are removing the multipath signals and then we are doing for the precise position. But another side, if we see that these signals, when it comes from the satellite and then hit the ground and then it is received by a receiver, so there will be a change of signal to noise ratio in when it is hitting in the ground. So it will be received by a receiver. So we can means what we can say, explore the possibility, what the parameters, or we can explore the how the information, we can extract the information from about the ground, what type of it is there, or what content, like soil moisture content. So we can find out the how much soil moisture will be there, volumetric soil moisture we can find out. So there are the two terms, the term GNSS reflectometry and the interferometric reflectometry are developing remote sensing techniques based on the reflected navigation satellite signals from water, ice, or land surfaces. IRNS's constellation of satellite are also designed to contribute. Means we can also utilize our Indian navigation, what we can say, navigation constellation, IRNS's Navig signals also. Any constellation we can be used. We have a two basically concept here. One GNSS reflectometry, another one is a GNSS interferometric reflectometry. In this reflectometry, what will happen? There will be a two receiver. One will be receiving the right-handed circular polarized signals directly coming from the GPS satellite to the this receiver, and another one will be receiving the signals, basically reflected signals, which will be the coming from the surface. It's called the reflected surface, reflecting surface, are left-handed circular polarized. So here will be having a two receivers. The SNR of direct signal will be used for the system calibration, and the SNR of reflected signal will be used for retrieval of geophysical parameters using power ratio of LSCP and reflected SNR over RSCP direct SNR. Alternatively, the approach of estimating reflection coefficient and reflectivity will also be utilized for the retrieving these geophysical parameters. Another is basically interferometric reflectometry. In that, what will happen? We are having only one receiver here on the ground. We are fixing at ground, and then we are seeing that the direct signals as well as the reflected signals both will be received by a one receiver only, which is set up at the ground only. So when we are receiving both the type of signals, the challenge is before us is that we need to segregate these signals and find out the reflected signals only. So because reflected signal only will carry the information of the ground only. So the interference of these two signals causes multipath, and as usual signal for GPS IR, the multipath signal constructively and destructively interferes with the direct signal as a GNSS satellite rises or sets. One can characterize the expected interference plate pattern from a horizontal panel ground reflection by a sine wave with a constant frequency, and the constant frequency depends on the height of the antenna face center above the reflecting surface h, and the GPS wavelength lambda, and the sine of elevation angle. Okay, so the SNR, what we are discussing here, the signal to noise ratio, that will be maybe changing when it is when coming from the ground, and we have to study this SNR only to find out the basically parameters, surface parameter. And this SNR will be depending on the various parameter. It is not only the basically height of the antenna, it is always the in what elevation angle the we are receiving the signals, GPS signals. Okay, and the wavelength, and maybe like GPS is operated on the L1 and L2. Similarly, the other constellations like Galileo, GLONASS, there will be other, so depending on the frequency as well. So these are the basically some few results just I'm showing to you. That's a reference from the Larson, and if you see that they have estimated the volumetric soil moisture, and you can see clearly it can be derived from the GPS signals. So we are also estimating this. We are having we are establishing our setup, maybe GPS network, different places, GPS stations, and from there the data collections is going on, and then after that we are also going to derive these parameters. So these are the references, and thank you very much. So here I will just summarize the things again. We have two types of maybe applications. One using the direct signals, GPS signals. Another one will be reflected signals. Direct signals, we can place our receiver on a ground as well as onto the low Earth orbit satellites. So when we are placing a ground, we can get the continuous measurements. We can place on the low Earth orbit satellites. The measurements will be maybe covering the global, but the thing, it will be sparse. It may not be the continuous measurements. Okay. Similarly, the reflected signals, if we see the we can when we place the receiver at a maybe over the maybe snow area, or maybe on the ground to find out the soil moisture or the snow depth, we can place this, or the only thing is that the signal should not be reflected from the other sources. So we place such a receiver as such a place where the no possibility of like buildings and other things should not be there. Okay, so these are the basically application of one more application of what we can say GNSS, and maybe tomorrow lectures the application of GNSS in the geosciences will be discussed. Today, thank you very much for joining us.